Is this working? Excellent. Hello. Welcome in this room after, I hope, a successful lunch break. I congratulate you on choosing the right session to attend to here. We're going to talk about functional data structures in Java. The emphasis here is on data structures mostly, and on functional in the second thing. My name is Oleg Šelajev, and I come from Estonia. And I work for the company called Zero Turnaround, where I am a developer advocate, which means that my main reason to exist in life is to care about the community of Java developers, go around, talk to people, see what the problems they have, and maybe share my experience and what I learned from talking to other people. I also maintain our corporate blog called Rebel Labs. I am a co-leader of a virtual jug, which is an online Java user group. If you're not members of that exciting community, you should totally join. And if you have any questions, or if you want more life wisdom, then you can find me on Twitter. I'd be happy to chat with all of you. If you check out the products that Zero Turnaround provides to Java developers, well, my employer would be happy. They would be happy. I will be happy. They will send me to talk to more amazing people to other conferences. So this is the credentials. Before becoming developer advocate, I was a Java developer for 7 to 8 years, so I have some experience. Just for you not to think that I learned everything from books. Let's talk about the functional data structures now. And when I was coming up with this session, I went on Twitter, naturally, and I made a poll about what people think the functional data structure, what does it mean? And there were some variants for the response, and I want to have like a small poll here. So who thinks the functional data structure means that it shouldn't be dysfunctional? So it should be like functionally correct. 2 people. Other people don't think it should be correct. That's an interesting. Who thinks it shouldn't be an imperative data structure? Good point. Functional imperative kind of are in a position. Who knows what a persistent data structure is, or thinks that the functional data structure should be persistent? 7 people. Excellent. And who thinks that it just means that the data structure allows mapping functions, kind of like in a Java Stream API way over the collection of elements, and that means the functional data structure? Cool. So hopefully, after the session, you will know more about what the functional data structure means, and judging by the response, I think we all can learn a thing or two here. Why I want to talk about the functional data structures is, and I want to reference a session from yesterday. Yeager gave a talk on the object-oriented programming, and he raised some points some people could call controversial. Some people maybe agree with that. But what that session makes you do is to think and revisit the foundation and the basics of what you know and how you approach software development. So you establish some mental models about how the software works, how you should write software, what are the tools for you to use when building software, like object-oriented paradigm or message passing architectures or something, and then you kind of use those, and that influences the way of thinking, and that influences the way you create software. So it kind of builds your vocabulary. So the more you know, the more successful developers you are, hopefully, or at least it doesn't make it worse. And this is, who knows who this person is? That is Ted Newert, and he has an excellent presentation on the pragmatic guide to functional programming. And in that, he explains the toolbox of functional programming, the actual functional programming paradigm, as opposed to object-oriented programming, and why you need that. And it is very fascinating. So if you are here for the functional programming part, I recommend you to find and Google that and find him. But let's get to the data structures. One of the blog posts that we created was the cheat sheet for Java collections, and we had this big kind of table of what options different collections have. Are they thread safe, not? And when we published that and started promoting that, some people responded, oh, the lack of functional collections is disturbing here, and it's kind of like sad that people don't know them more. And that was my main motivator to create the session, to come to different conferences and educate people about the existence of functional data structures, and that you can use them in your Java programs, and that you can successfully use them. So with that, this is the next slide. Why do we need data structures? It's very simple, right? So they power our programs. This is where we hold information. So almost any program will have some sort of a collection in there. Do you know if you can write a Java program in a way that it doesn't load the Java util list class? Who thinks it's possible? Who thinks it's impossible? So the Java util list is always loaded. Who doesn't listen to me and drifted off? Excellent. This is the puzzle, a question with a star for very advanced students. So there is a saying, I think by Henry Ford, that you can write efficient programs in any language as long as that language is imperative. And the reason for that is that there is a massive body of knowledge about data structures and how to organize computation and algorithms to operate on those. And well, the books are there, so you can just learn the algorithms, put them, translate into your language, and kind of use that. And the only catch is that all that knowledge exists and the examples for the imperative languages. So if you use a different concept, so if you want your programs to be more functional, it will be very awkward to operate on normal data structures. So if you imagine a normal binary tree and you would like to traverse that in a functional manner, maybe it's not that convenient. And then you start updating that and the whole world goes crazy. And your programs not become simpler, but they become more complicated. So, however, there are plenty of research about the functional data structures, which are the implementation of the normal collections or trees or maps that are very suitable for use in a functional programming language environment. When we talk about data structures, we're going to talk about mostly collections, because the collections library in Java is what we use to hold data. So we have lists and whatever, and there are multiple flavors of data structures there. So a little bit, I'm going to use the data structure and the collection interchangeably, because they both mean the abstraction that can hold elements in some shape and form. So the most basic block is, and the most basic and known type of data structures are the mutable data structures. The Java collections library is full of mutable data structures, mutable collections. How do you know that? You just look at the API, so you can look at the collection interface, and you find methods like that, and you see that some methods have void as the return type, and that means that they operate on some state, and they mutate that state. They do something, and they produce a side effect. So they do not just return the value back to you, but they accumulate some computation information. They put this somewhere. So they mutate the internal state of the collection. So there are methods like add all, and they return Boolean. And it also means that they store the elements within the collections. They mutate the internal state of the collection. Sometimes this is the easiest, the fastest, and the most natural way to do things. Sometimes it is not. Honestly, after some time of thinking about this, I figured out that probably if you have an API and you have the methods with return type of being void, that could be seen as a small code smell. So probably if you have those methods, you can look at them very suspiciously and figure out what state they mutate. And you can figure out that that could be a problem for multiple mistakes and bugs. Especially if you operate in a concurrent environment where there are multiple threads operating on the single data structure. You want to read and write data from there. You will have to work a little bit harder to ensure that it's correct. The Java collections library also comes with the implementation of the immutable data structures. So the immutable data structure is the one that doesn't change its internal state. So once it is created, you cannot afterwards execute methods on that, call some operations, and then the state of that data structure doesn't change. So you build a list once, and then you cannot change that. In the Java library, what you do, you have the wrapper methods, and you can pass any collection and call the collections unmodifiable list or unmodifiable set. And the returned object, it will still implement the collection interface, but when you will call the mutating methods, it will throw exceptions. So if you do that, you are one step closer to writing programs you can easily reason about, because now, even in the concurrent setting, there won't be any surprises for, oh, why my list is suddenly empty, or why the two elements were added but only one registered, because nobody can change that. And the third type is the persistent data structure. So the persistent data structure is the one that you can run not the mutating, but you can change the data structure. But what it does, it creates the new version of itself. So it stores all the versions of itself that you wanted to execute operations on. So if you have a tree and you want to add a new element, it will return a new version of the tree. So, and it will persist and give you access to all the previous versions of itself. So for the efficiency purposes, typically the implementations will try to reuse as much of the internal structure as possible. So on this example, if we had the black tree and then we add the blue node there, or we change that node, you can see that it changes on the necessary pass here down, but like the left node to the B stays unchanged. So that part of the structure is reused. The functional data structures are the ones that are immutable and persistent. So this is the definition of what a functional data structure is. So once created, it doesn't change its internal state. You cannot mutate that. So that makes it very easy to use in the concurrent setting. It makes it very easy to reason about what the current state of the data structure or a collection is. And when you call operations on that, and if they require to change the data structure, you will get back the new version of that. So that's a functional data structure. The problem with implementing functional data structures is that first, since it's immutable, it has to be immutable. It's not that easy to implement without reassigning things back to existing items or nodes or abstractions within that. So if you have a tree and you need to change the value of a single node in there, it's very easy to do when you can reassign things and destroy the existing structure. The second thing is that the persistence property, the one where you have to provide access to all the past versions, it seems very expensive from the performance point of view. We all want our programs to be fast. We all know that it's very easy if you change such a low-level thing as a collection implementation. If you change the implementation of array list, it's very easy to introduce performance regressions. So if you swap that for something that has to maintain this past state, then it just feels that this would be terribly, terribly slow. Who thinks it will be slow? Who thinks it will be terribly unusably slow? There are three people think that it will be unbearably slow, just for the record. So in this session, let's talk about how to build certain data structures, and let's talk about if that is actually slow and exactly how slow that is. So the simplest data structure that we're going to talk about is a list. A list is a sequential collection of elements where you can have the index and they come in order. So the immutable list, or typically called the cons list, is the class that looks like this. So it implements a list interface, and let's not talk about if that list is the actual Java util list or not. But to implement the list, you have to have access to three things. The first element of the list, called head, and the rest of the list called the tail. And since we know that the list will be mutable, we can introduce things like final variables for the lengths and stuff, because we know it's not going to be changed. So we can introduce some performance optimizations just by design from the very beginning. So when you have a list like that, we can implement the operations that mutate that list to produce other collections for us. So if we want to prepend the element to a list, what we do, we cannot change the existing list, so we cannot change this instance. But what we can do, we can return the new list that will consist of whatever we had before, this instance, and it will come as the head of the new list will be the element we're prepending. So the result will be just the new element and the tail. As you can see, the code is super simple, like super straightforward, and it doesn't do much. So it cannot be that expensive in terms of performance. If you think about if you use this list and you prepend something, then you will get the new value back. So you get the new object back. But the existing instance is not changed, so you can prepend something else again. And since they reuse the tail, you can have the operation and the state where you have multiple modified versions of the original collections, and they will reuse as much state as possible. So that was one of the things that we talked about, how to make persistence work a little bit better. You reuse the structure. You can introduce more complex operations on this very basic structure of the head of the tail. So for example, you can fold the list. If you are not familiar with the conception of folding a list, you just imagine a list of paper or a carpet, and you kind of start rolling it in, and you roll it one element at a time. So fold left comes, you fold from the left. Yeah, from the left from you, from the right from me. The implementation of functional collections and functional data structures does not have to be as pure as many people think. So what you can do internally, when no one is watching, you can use the normal iterators, you can use the normal collections, you can use additional collections inside if you need a helper list or something. You can use normal mutable data structures there. Just because when nobody is looking, if you do not publish your data to everybody in a way that it's still mutable, then effectively it is immutable. So in this method, we can just, to fold the list, what we do, we iterate over the internal condition, we have the accumulator element, and we apply a function on every element and collect the data. Why do we need those? Because with very simple operations like that, we can implement other useful collections operations. So for example, reversing a list. And we talk about this because we need to talk about the complexity of operations. So reversing a list, very simple. You just fold a list using the prepend operation. The code looks very simple. The main point of this slide is to show that the code for the functional data structures is super simple. Typically much simpler than the code that is written with for loops over some indexes and over the rebalancing nodes operations. Appending elements to the list is also available. The thing is that you have to fold the list from the right, from the other side. The problem with this is that not all operations on the functional data structures are equal in the performance point of view, from the performance point of view. If you have just the head of the list and the tail, accessing the head is very cheap. You just read the value of the head. If you need to access the tail of the list, the last element, that is expensive because you have to traverse the whole list. So when we talk about appending stuff to the list, this would be an expensive operation. In terms of how we assess what operations are expensive or not, performance-wise, we have the algorithmic complexity. Who feels that they are very familiar with the terms of algorithmic complexity? Who thinks they are not very familiar with those? Excellent. So let me quickly explain. So the algorithmic complexity of the operation is the measure of how effective, how fast or not fast the operation can be. How much time can it take in terms of the smaller operational steps on the input of the arbitrary size. So imagine if you have like a very short list and you want to reverse it. Probably it would be very fast, whatever you do, because it's just a very short list and computers are fast. The same way, kind of the same way when you write your application on your local developer's machine and it's very fast because everything is local, there is no data, and everything is fast. But in production, it could be slow. So when you have a large list with millions of elements, reversing that could be slow. But it's hard to explain exactly how slow it is. Because if you have a list with 1 million of elements, it could take like 5 seconds, or another machine could take like 2 seconds, and it still could be slow or not. So the algorithm complexity explains how slow the operations are in terms of the function from the input size. And there are a bunch of notations, so it typically comes with a big O notation, and there are kind of buckets of how slow the operations are. The best complexity would be the constant, which means that the operation takes a fixed amount of steps to complete. So when we talked about creating and prepending an element to a list, we just had one expression saying the new cons, and we just pointed to some values. We didn't compute anything. We can finish that operation in a fixed amount of steps. That would be a constant complexity. So for example, the linear complexity here would be the operation that finishes in the linear number of steps of the input size. So we have an input size of list of 3 elements, and it finishes in 6 steps. That is a linear complexity. But if the same operation on the million list finishes in like 2 million steps, that is the linear complexity. So the larger your collection is, the slower it is with the linear growth. There are obviously some operations that are slower than that. If you have to look at the elements more and more and more and say compare elements pairwise, you can get to the quadratic complexity and so on until you get to the buckets where the operations are so slow that they actually hardly finish on larger inputs. Besides that, there is the amortized complexity notion. The amortized complexity is when you have multiple operations on a single data structure, like you call, for example, prepend multiple times and then you call the reverse. You want to assess how slow that is together. So not just individual operations. And this is a very, very important concept, because without that, we would think that functional data structures are really slow. So imagine we have a list and a set of operations like that, and we'll talk about the BANKER'S method for assessing the amortized complexity. So the cost of the operations, the algorithm complexity for those operations, is the linear for the prepend, and the constant, sorry, for the prepend, and the linear for the reverse, because we have to get to the very back of the list at least once. Now, for the BANKER'S method, what do you think? You assess every operation as having not the complexity that it has, but a little bit of credit, the alpha, for every operation. So now our total complexity of all those operations will be linear in size and n times this credit that every operation gives you. And the reason is that if you make those operations happen and you accumulate that credit, that you counted that, oh, you spend that time, you spend that number of operation, but you actually haven't, because it's just a imaginary concept, then you have that credit to spend on the expensive operation. So now, with adding those tiny alphas to all the operations, what we can do, we can then simplify the resulting formula here. And we simplify that, and this is a constant. So it's a very small alpha and just a multiplier of 2. So now with the rules of the algorithm complexities, we just typically ignore the constants. So it just disappears. And then per operation cost, if we divide O(n) by n operations, the per operation cost will be the constant. So this is how BANKER'S method work. But what it shows you that if you look at the set of operations and you want to assess the complexity of that, you could get much better results that are more reasonable for practical applications. So if you look at the reversing the list in isolation, it could be seen slow, but in practice you will probably create that long list first before reversing, and then it would be kind of normal, which is very good. So that's how you create an immutable functional list, and a functional assess how slow it is. However, another argument here is that if you have the access to all the versions of the data structure before, because it's persistent, you can create the list and then call the expensive operations again and again and again. So you build the list once and you call the reverse, and then you take the previous list and you call reverse again and again. And that will ruin our BANKER'S method calculation, because now we don't have those credits that we accumulated building the list. And it is a problem. To solve that problem, we need to figure out how to evaluate our expressions properly. So there are multiple modes how evaluation works. You can have a strict evaluation when you pass the things. You can evaluate things by value. You can memorize the results. You can be lazy. And what we want to have, want to have the call by need evaluation mode. So it should be, the evaluation should be lazy. So unless you need the result, you don't compute that. And you also should memorize the results. So it helps that in the functional world, you typically have pure functions that depend only on the inputs. So if you reverse a list once and you store the result, if you memorize the result, next time you know that the reversing the same list will give you the same result. So you can just reuse that. It gets into this land of the referential transparency, but we are not going to talk about that. So you can Google about it and educate later. But what we want to have a lazy evaluation strategy, and we want to have very easy way to memorize the results of the operations. Let's look at the different data structure because list is boring. So who thinks they know how to build a queue? A queue is like the opposite of a stack. A first in, first out kind of collection. So we want to build a functional queue, so we would like to build it in a functional way. So how to build a queue when you have a functional list? So we have the implementation of list, now we want a queue. Who thinks they can do it? Who thinks they cannot do it? Okay. See, not pessimistic enough. So very obviously, since the only thing that we have is the list, we just create a class queue and we put the list inside and we say the head of the list is the head of the queue, the tail of the list is the tail of the queue, right? The end of the queue. But it's very inefficient because you need to access from both sides. From a queue, you need to take elements from the front and you need to append elements on the back. So appending elements to the list is very inefficient. It's not very inefficient, but it has the linear complexity. So because you need to traverse that list again and again. So this would be slow. So how do we solve this problem? Since the only thing that we have is a list, we add another list and we make a queue out of two lists. So we'll have the front of the list and the rear of the front of the queue and the rear of the queue. There is a catch that we not just hold the elements in order, but the rear of the queue is in the reverse order. So if we have a queue 1, 2, 3, 4, 5, and it's separated between those two lists in a way that the front holds 1, 2, 3, that is in the normal order. That gives us access to the front of the queue very easily. And the reverse of the rear of the queue in the reverse order, so then 4 and 5. Why is that is good? Because that gives us access to the rear of the queue, to the very last element easily. So we can prepend, we can append elements to the queue very easily, and we can access the head. So this is a very typical trick where you come by a mathematical solution to a problem, and then you just code it, and then the code will be much easier. So to enqueue an element to the queue like that, what we need to do, we reuse the front of the list, and we just take the rear of the list and we prepend element. Because our queue, the last bit is reversed, we utilize very fast, very efficient operations on the list to access the end of the rear of the queue. And you can see that this operation will be super cheap in terms of the computational steps, because this is a constant and this is just creating a new object. Boom. So enqueuing elements is very easy. Accessing the tail of the queue is also very easy. So the tail is everything besides the first element. You just, well, access that directly using the API of the underlying collection or the list. You can find and see the head element of the list. That is also very easy. You just look at the front of the list. However, what will happen if the front list is empty? We throw an exception there because it's empty, but there is a catch because we have the front list and we have the rear list. What happens if the front is empty and the rear is not? We need to access the end of that rear list, and that would be inefficient, right? We have to work around that situation. Luckily for us, we designed our queue in a very intelligent manner. It is, well, let's look at the DEQUEue first, because that's how you make the front empty. So you take the elements from the front of the queue. Two things to notice here is that first, you cannot just follow the interface for the Java collections library, because for the functional collections, you cannot have those mutating, void returning operations. So you will have to have different interface, which makes the adoption of those harder for you. But you can just easily have a tuple class or a pair class and return the head element of the queue and the new version of the queue, the result after the dequeuing element. And then after that, you can use those elements independently. So to dequeue an element, we just need to take the head of the queue and return that as the value. And the new queue would be just everything besides the head. So we just remove one element. And we'll look at how to implement those. But if the queue is empty, we throw an exception saying it's empty. So what we want to maintain an invariant. An invariant is something that holds true at all times. So our invariant will be that the queue, the front list, the front is empty only when the whole queue is empty. So there will be no queues where the front is empty and the rear is not. How can we ensure this invariant? Seems hard because we can dequeue elements, right? And it will take elements of the front. The immutable data structures to the rescue. Since we don't mutate the queue, we don't mutate the internal state. The only place where we need to maintain this invariant is when we construct the new queue, because that's the only place where we manipulate the state. And when we construct the new queue, and where in Java code we construct the new queue, inside the constructor. So we just need to add a bit of logic inside the constructor and say, if we want to construct a queue where the front is empty, then just please reverse the rear and put it back. So why is this cool? Because first it shows you that working on immutable data structures is very easy, because you can reason about that. You can build a number of invariants that you want to hold true about your collections or data structures at all times. And then you use those invariants to reason about when and why you have to do things. The second example is that reversing the list is expensive. It's a linear operation. So if we call this very often, then our queue would be slow. We don't want it to be slow. We want our software to be fast, after all. Not sure why. We want it to be reasonably fast as our specifications require. Sometimes faster, just to show off. So the reverse is not expensive operation because of the amortized complexity. So imagine you have a queue like that where you have m elements in the front list and m elements in the rear list. So to get to the code that actually will reverse the rear list, you have to call at least m dequeue operations, because they take one element at a time. So you call m operations that are constant complexity, and then you call a reverse that is linear. And as we know, if you have a number of constant time operations followed by a single linear time operation, the whole group has the amortized complexity of 1, of a constant. So with this simple mathematical trick, you can ensure that your implementation of the collections in the real application, so when you actually use them, will be bearable. Who knows how to build a map? A map is the mapping between the key and the value. Who thinks they know how to build a functional map, which is immutable and persistent? Let's simplify this. Just a couple of people. You have a list and a queue, because you have those. How to build a map if you have a list and a queue? True, it's very hard. It's actually pretty impossible to implement a map if you like a functional implementation of a map if you have just a list and a queue. You probably can do that. It won't be very fast. And probably you would not like to use that in your code. So to implement a functional map, typically what people use is the hash array mapped tree, where the tree is the prefix-based tree. It's a tree like T-R-I-E, tree, that tree, not just normal tree. What it has, it looks like a normal tree, but for the keys, the path from the root to the leaf node encodes the key. So if you have a key like that, you split it into a bunch of small sectors, and based on that, you pick into which children traverse. So to get into this, to get the value by this key, you get into the green node, then you get into the orange node, then the lilac, blue, and so on. And then and the leaf of that tree will be the value. So this means that the operations, when you implement that, would be fairly efficient, because it depends only just the length of the key. And if you use something like integers, for example, then you only have like 32 bits. So the depth of your map or depth of your tree will be 32, which is a constant. If you need to update this data structure, you do that the same. You create the new version of the map, and you just reference as much as possible the old ones. And it looks a little bit confusing, but it works exactly the same way as we looked on the queue. You reuse the stuff. You just point to where the parts of the map are, and you create the new structure, and you return that. With this way, you satisfy the property of the state structure being immutable. And since you still have the access to the previous version, it's persistent. Let's talk about trees. Who knows how to implement a red-black tree? Few people. Great. Who knows what a red-black tree is? It's a balancing binary tree, and there is an algorithm. I'm not going to talk about the red-black trees in the functional world, but I want to talk about how to represent a tree in functional data structure that helps people work on the tree structures. So if this is the tree, and this is how you imagine a tree, then the trick is that often you can change the perspective, and this will help you to do something. So if you think of a tree as a structure called a zipper, what it is basically the data structure that you have with your location, where you currently sit in that tree. So at every given moment, a zipper would be, say, a tree and the pointer to where in this tree you are. So you will have the both children from this, and you will have the path to the node. And then when you traverse the tree, you will create a new zipper and say, if we go to a different child, you have the children, and you say that, oh, we are in this tree, but we sit in that node. If you think it's inconvenient to think about this and work with the zippers and trees in that manner, I show you the file system structure, which is exactly kind of the same the thing that a zipper on a file system tree. So you have your current location, you have the pointers to what are the children of those, and you have the pointer to the top. The trade-off here is that you spend some computational operations when you traverse the tree. Traversing the tree means creating the new zippers. So when you go one level down, you have to create the new object to say, oh, I'm now in this tree, but at that location, which is a little bit inconvenient. But it's a very typical data structure to use. And if you want to learn about those, zipper is the thing that you should Google. There are a bunch of implementations in the Java. Probably you're going to use that. If you're actually going to use that, you're going to use that when you traverse an XML document or a JSON document, something like this. So that is the zipper. Now, all that goodness, the functional data structures have been accessible for you in multiple programming languages, where people think that their language is better than other languages because it offers more functionality, despite being as powerful as any other language. So there is the implementation of functional data structures in Clojure. There is an implementation of the functional data structures and collections in Scala. Luckily, now we have the implementation now and since some time in Java as well. And since Java 8, we can use Lambda, so it actually even working with those, the code looks pretty reasonable. So welcome Java slang, or as they try to allegedly register. So you cannot call your things with Java in it because Oracle doesn't like that. So when you grow large enough and people start to recognize you, then you can get into the lawyer debates about if you can use that name or not. So they were known as Java slang. They renamed themselves recently into what people call waiver. Personally, I don't know how to pronounce that. So being a Russian from Estonia, I typically pronounce things the way they're spelled. So it's V-A-V-R. So I call it Vavr. So just like Stanislav Wawrinka, the tennis player. So official version is that it's waiver. So this is the library that comes with the multitude of functional data structures for you, and you can just look at that code. It's all implemented for you, so you don't have to actually implement all that goodness, all those queues and maps and vectors and arrays, and you can just use them inside your application. So there is very many classes that you can use. It doesn't exactly implement the interfaces of the Java collections library. Why is that? Because as you saw, for example, for some data structures, it's just impossible to be functional and conform to that interface, like with the queue, for example. But it does implement a very sensible API, and it's very nice to use. On top of that, it offers a bunch of additional utility classes and helpers. And after this session, or maybe on the next slot through the next session, there will be the talk on using Vavr by Gregor's, and he will show you exactly how to use that API, what that API looks like, and show that goodness. So I recommend visiting that talk as well if you enjoyed this one. So one good thing, there are multiple implementations of the functional data structures. Why I like Vavr and or Java slang, so one thing that makes them great is that they really want to make this library great. And what they do, they also have a bunch of benchmarks inside the repository, just with the source code. So you can download that, you can run that, you can assess how much slower, say, a Vavr queue priority queue is than the normal priority queue. You can implement the same way they implement the benchmarks to see what it will be for your use case, and you kind of can very easily assess, like, will this be a reasonable trade-off to have a more readable code with working on collections versus maybe a bit of performance penalty and overhead. So the benchmarks work in the repository work like that. So they have a bunch of implementations of the data structure, say a priority queue, and they have the JMH classes that create the collections, the containers of a certain size, and then they execute operations on that. So for example, on the priority queue, what you can say, well, let's enqueue 10,000 elements and see which implementation of a priority queue is slower, and then see the ratios. So kind of like that. You can dequeue stuff the same way, and just wanted to show you how the dequeue API works. So you get back a tuple, and then you access the result and the rest, the new version of the collection at hand. Or you can, I don't know, have a more complicated benchmarks where you actually try to figure out if the performance in a certain load of operation would be reasonable for or not. So for the priority queue, if you just put elements in, take elements out, you will get them in sorted order. So, and you can look at the code in the GitHub repository very easily. So if you run that, you will get a table like that. So the benchmarks are created using the JMH. So they are, that's the first sign that they are not that unreasonable, or at least the first step to being reasonable as benchmarks go. And the results that you see here may vary for you. They are also a little bit old, so I'm not sure what's the current result that you get from the current master of the branch. But if we talk about the priority queue, and if we talk about the certain benchmarks there, then it could be a little bit slower than the blocking version of immutable priority queue in Java. You would like it to be blocking because you would probably use it from the concurrent setting. It is a little bit slower than the immutable priority queue in Scala, but not incredibly slower. And it's also a little bit faster than the persistent implementation of the priority queue from Scala Z. Are those numbers true. Nobody knows. What they don't take it for granted. But what they show you is that actually the implementation of the functional data structures could be reasonably fast. So yeah, there is some performance overhead, but then, well, what people say that C code could be, I don't know, twice as fast as Java code or something if you manually optimize that. Maybe you need that. Maybe you need the last bits of performance in your code. Maybe you don't. So what I want you to think about is that to assess the quality of, assess the performance overhead based on your particular needs. So don't think it's slow. Look at the API. Check this out. Google the terms that you didn't recognize from the session and become smarter and more valuable as software developers. I know it's a questions time, but I'll just finish it very slowly. So the object-oriented code tries to make itself understandable by encapsulation. The functional programming tries to minimize the moving parts. So with immutable data structures, with functional data structures, there are very few moving parts when you talk about collections. So it's great. If you want to know more, there is a book called Purely Functional Data Structures. It's, I think, published in 1998, based on the PhD thesis of Chris Okazaki, which he published 2 years earlier. So you can think that it's like a book is 20 years old, which it is, but it still is an amazing book. So it goes through what we talked here in more detail. It actually presents a coherent explanation for all those things. So if you would like to learn more, this is probably the book to learn for learning the basics. If you just want to check what data structures are available for you, like in general, like what humanity has come up with, I recommend this Stack Overflow answer to the question. And you can see that the question is like, what's new since that book has been published? So what is new in the last 20 years? Just this shows you that that book is a classic work on the functional data structures. And the answer is incredibly great. So you can just go there, there are plenty of links, explanations, links to papers and everything. So if you're interested, boom, just, I'll make the slides available, so and the conference will make them available, so you can do that. So with that, if you have any questions, we have 8 minutes for the questions. If you don't have any questions, then find me online and ask them there.
I see that even for simple list, we create a lot of objects. What's garbage collector opinion on this?
That's a good question. There are different implementations of the garbage collection. And yes, since we want our data structures be immutable, we cannot just modify things in place. So we have to create new stuff. So we have to create garbage. It is more memory inefficient, less memory efficient than immutable collections. And so for some workloads and some domains, it would not be the best choice. But if your code works, if your code is structured in a reasonable manner, and you have those mutating operations locally, so you create new objects, they are created, then you do something with them. You maybe traverse and compute the values, and then you discard those objects, and they die young, as most of objects. Then the garbage collection should be able to keep up with that. You will have to run the benchmarks on the workloads and on the collections that are of particular interest to you, but that is the question to the implementations of the garbage collection rather than the functional data structures. We program as if we have infinite memory. That was the promise. And we should totally do that. But yes, it is heavier on memory. Any more questions? I can repeat, but if you have a mic.
Well, is anybody?
Yeah, the first row, gentlemen.
In modern Java, we use a lot of frameworks and libraries which operate with normal collections. So, how are we supposed to use those unmodifiable collections, especially with the fact that they don't even share the common interface with the normal collections?
That's a good question. The easy answer to that is you have to rewrite code. So it's not a drop-in replacement because of the API incompatibility. So it's not like you can just like include the Maven dependency and then just grab your source code and say, oh, array list is now cons, and enjoy, and you just run the load test and see if it works or not. So you will have to carefully rewrite the parts of your code that use collections. It will be harder with the frameworks. There are a number of, so for example, for the Vavr, there are a number of projects that use that successfully. There is, for example, a circuit breaker implementation based on Vavr. So you can replace maybe some higher order libraries with the analogs. Or since you probably don't want to just drop in the replacement of the collections as is anyway, because of some performance implications, you want to assess which parts of code you want to rewrite using that. You want to assess the performance penalties that you'll get. So this will still be the manual work. But for some applications, it would be very beneficial. The concurrent access to stuff is simplified. Your code becomes much more simpler. You don't have to manage state. If you have small, I don't know, say a microservices-based architecture of your whole system, then you can start with maybe experimenting on one or two and then grow that usage over time, if you like it. If you don't like it, and if you write code using the normal mutable data structures and you never have any bugs or problems because of that, keep doing that. Keep doing that. Keep doing that. Keep doing that. Keep doing that.